rules for exponents. Now, we've talked about exponents before, and what we're going to do is we're going to look to a couple of key properties of exponents. There are a lot of important properties of exponents. We're going to look at two of them in this section. I want you to consider the example that I have where it says 2 raised to the 4th power times 2 to the 3rd power, which we sometimes say is 2 cubed. Remember what 2 to the 4th power means. It means 2 times 2 times 2 times 2. And then I'm going to multiply, big old dot there for that dot right there, 2 to the 3rd power, which is 2 times 2 times 2. 1, 2, 3, 4, 5, 6, 7 factors of 2 gives me 2 to the 7th. Now look at this, and this, and this. Is there a relationship between those three numbers? Well, sure there is. 4 plus 3 is 7. You can see you have 4 factors, you have 3 more factors. That gives you a total of 7 factors. So look at the product of powers property. A to the m times a to the n is a to the m plus n. As long as the bases for the exponential expressions are the same, you can multiply them by adding the exponents. Look at the examples that I have. 5 to the 3rd times 5 to the 2nd. I keep the base the same, 5, and I add the exponents, which is also 5. So my answer is 5 to the 5th power. If I look at the next one, I have 3 things that are being multiplied, all base 7, 7 to the 2nd, 7 to the 3rd times 7, which is the same as 7 to the 1st. So this is 7 to the 2 plus 3 plus 1, 7 to the 6th power. Even with when the base is a decimal, this is 0.4 to the 3rd, this is 0.4, which would be, again, with no exponent, it would be as if it was to the 1st power, and that this would give me 0.4 to keep the base the same, but you add the exponents, and that's 4. Now down here, I have 9 to the 7th times 9. Again, it's like 9 to the 1st. When the exponent isn't there, it's understood to be a 1. This is 9 to the 8th power. Here I have x to the 10th times x to the 2nd. Now, all these other problems had numbers as the base, but here the base are exponents. Are variables raised to different powers as exponents there. So what I'm going to do here is I'm going to work them just like with the real numbers. These variables, I'm going to keep the variable the same. It's the same variable in both for the base. I'm going to add the exponents, 10 plus 2, x raised to the 12th power. Now here, this problem is a little bit more like this one. I'm going to do this one before I come to this last guy here. X to the 9 times x to the 3rd. Again, keep the base the same, add the exponents, x to the 12th. Okay, same answers I got here, just slightly different problem. But here I have coefficients. This is a monomial times another monomial. You multiply the coefficients, that's 14. You multiply the variables that have the same base here, the exponential expressions, by keeping the base the same. Don't multiply the exponents, you add the exponents. 14m to the 9th power. All right, that's the first property of powers, the product property of powers. And so what we're going to do now is we're going to look at one that's a little bit different, but kind of goes hand in hand with this. Now let's consider this example. 2 to the 6th all over 2 to the 2nd, which is the same thing as saying 2 to the 6th divided by 2 to the 2nd. 2 to the 6th, remember, is 2 times 2 times 2 times 2 times 2 times 2. 6 factors, and 2 to the 2nd is 2 times 2. This factor of 2 cancels out with this factor of 2. This factor of 2 cancels out with this factor of 2. There's nothing left in the denominator but a factor of 1. I have 1 times 1 times 2 times 2 times 2 times 2 all over 1 times 1, which is 1. 1, 2, 3, 4. This is 2 to the 4th power. Now look at this exponent, look at this exponent, and look at the exponent in my answer. You see a relationship, I hope, between those three numbers, because if you subtract these two numbers, you get that one. And that's where the quotient of powers property comes into play. A to the m divided by a to the n is a to the m minus n. You subtract the exponents, top one minus bottom one. And this, of course, is where a is not equal to 0. So let's look at these examples and use this property here. 5 to the 8th divided by 5 to the 3rd is 5, 8 minus 3 to the 5th. 10 to the 11th divided by 10 to the 7th is 10 to the 11 minus 7, 4th power. Now this one's a little trickier because I've got coefficients here. that I have to deal with along with the variables. I can see that I have a 12 and an 8, and just like with a regular fraction that simplifies, I can divide top and bottom by 4. This would be 3. This would be 2. And then I have exponents, even though it's not written there, it's assumed to be a 1, so I have 8 minus 1, that's 7. I have 3z to the 7th all over the 2 that's in the denominator. That's all that's left in the denominator is the 2. And that's kind of unusual looking, but that's my answer there. Something very similar to that. I have coefficients, I have variables. 7 goes in the 7 once, 7 goes in the 21 3 times, so that's 1/3. But I have c to the 9th on top, c to the 3rd. They have the same base. You subtract the exponents. 9 minus 3 is 6. This is going to give me c to the 6 all over my denominator, which is a 3. And this is my answer right here. Check the parts out. The 3 is in the denominator, and 9 minus 3, the c to the 6 is in the numerator. Here, 8 goes in 8 once, 8 goes in the 32 4 times. I have 5 factors of d on top, 3 on the bottom. 5 minus 3 gives me 2, so this is equal to 4d to the 2nd. Nothing in the denominator because everything canceled out except the factor of 1, and you don't need to put it over 1. Now this one here, I've got to do 2 steps to work this one out. I've got to simplify the numerator by multiplying like I did in the first half of this lesson, and then I'll divide. This is 10, a to the 4th times a to the 3rd is a to the 7th. Remember, we add the exponents when we're multiplying. And this is divided by a squared. Now, just like I did in the last problems, 7 minus 2 gives me 5. This is going to be 10a to the 5th. That's my answer. 2 steps there. 2 steps here. I'm going to simplify the top. X to the 4th times x to the 6th. That's 5x to the 10th. You add the exponents. And that's all over 10x to the 5th. Well, kind of like what happened here and what happened here. 5 goes in the 5 once, 5 goes in the 10 twice. I have the same variable. Subtract the exponents. 10 minus 5 is going to give me x to the 5th all over 2 because I have a factor of 2 in my denominator. Over here, I have a negative on top, a positive on the bottom. Don't let that worry you. I do notice that 4 goes into that 3 times. And 4 goes into that 4 times. Oh, I jumped the gun there, didn't I? I need to multiply these together first. This is negative 16t to the 10th all over before I start canceling there. 12t to the 7th. Now I'll divide 2 by 4 into that 3 times. 4 into that. There's a negative there, negative 4 times. And 10 minus 7, that's going to give me a negative 4. T to the 3rd, 10 minus 7 is 3, all over 3. It's getting a little bit messy there. Now, some of the problems are stated this way, but they mean the same thing as what we've already looked at. You'll just be adding the exponents to find the missing exponent here. In this case, this would be 11 plus 6, 17. A little bit more of a challenge would be if the problem has this as the missing exponent, because then you'd have to see what would you have to add to 11 to get to the 17, and then you can see it would be the 6. Okay, these problems, although not the easiest ones we've come across, are not by any means too difficult for you to do. You just need to remember your rules, and you need to practice, practice, practice.